Hi everybody, welcome back to another chemistry tutorial video. Today we're going to be talking about hydrates. Alright, before we go any further, you're going to need a couple of things. Make sure you have your periodic table. Make sure you have your calculator, and make sure everybody has the hydrate worksheet honors. It should say on it, hydrate worksheet honors. Go ahead and do that now. Brilliant. All right, assuming that you have that and you're following along here with me, I want you to go ahead and just follow along as I read this paragraph here. A hydrate is a compound that has a specific number of water molecules bound to its atoms. Hydrates form when certain chemicals are exposed to the water in the atmosphere. The hydrate can absorb the water, bonding the water with the cation in an ionic substance. Okay, let's go ahead and pause. Hydrates require two things. The first thing that they require is an ionic substance. Ionic substance. You will remember that an ionic substance will be formed from a metal cation and a non-metal anion, or they will result from one of these things being replaced by a polyatomic ion. Or in some cases, both of these things can be replaced by a polyatomic ion. Great. The second thing that we need here is water. As you'll remember, dihydrogen monoxide, H2O. And here's what happens. We have a very positive cation ionically bound to a very negative anion. This is our ionic substance, sodium chloride. And we also have water. You'll remember that water is very polar and will form two partially positive locations and one very, very partially negative location. And what's going to happen is that the sodium chloride is just going to be sitting there, and a water molecule will pass by in the atmosphere and will form a very strong attraction to that cation, to the positive side, right? Remember, cations are positive. Great. When ionic substances do this, they're said to have, the word is hygroscopic. Hygroscopic, the ability to pull water out of the air. If any of you have ever had salt kind of like cake up in your salt container, whatever it may be, and it forms these large clumps, it does that because it's pulling water out of the air, and it's actually changing the chemistry, it's changing the properties of that substance. Right? We call that hygroscopic. Great. Let me go ahead and continue reading. I'm starting at common examples. Common examples of hydrates are gypsum, calcium sulfate, dihydrate, borax, sodium tetraborate, decahydrate, and Epsom salts, magnesium sulfate, septahydrate. Gypsum is a mineral that is mined and used as a fertilizer, as well as the main ingredient in chalkboard chalk and drywall. It's kind of cool. Borax is a household cleaner and a laundry detergent booster, and Epsom salts are used in bath waters to relieve pain and inflammation. Hydrates can exist combined with water or in their anhydrous, or without water, form. Great. So when we have our ionic substance here bound to water, it's called a hydrate. And it is said to be hydrated. However, if I were to add fire to this, what would happen is it would drive off the water, and we would get the anhydrous form, which would just be the sodium chloride by itself, no water at all. All right, let's continue on. Hydrates are named by the formula unit followed by the number of water molecules. The number of water molecules are given the prefix of mono, di, tri, tetra, etc. Okay, so now what we're doing here is we're kind of combining what we know about naming ionic substances and what we know about naming covalent substances. Okay, if this is getting a little bit confusing to you, please feel free to set up some office hours with me so we can chat about this. Let's continue on. For example, CaSO4.2H2O would be named calcium sulfate dihydrate. Okay, here's how we do that. Whenever we are naming a formula unit, we're doing a couple of things. The first thing that we're always going to be doing is we're going to name the cation. Remember, the cation always comes first. Then we're going to name the anion. Great. We will always do these two things. Always, 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 always. Now, there's a couple of exceptions here, some additional steps that we may need to take. If the anion is elemental, that is to say it's an element, then what do we do? Hopefully you remember. We change the ending to IDE. Whereas if the anion is a polyatomic ion, then what do? We do nothing. We leave the name as it is. Do nothing. Great. Sometimes with names, or sometimes with ionic substances, the cation can have more than one potential charge. It can have more than one oxidation state. In the event that it has more than one oxidation state, what do? Right? If the cation is a transition metal, we need to acquire the oxidation number. And how are we going to do that? We're going to do that with Arabic numerals? No, we're not going to do that with Arabic numerals. What are we going to do that with? We're going to do that with Roman numerals. For those of you who are confused, Arabic numerals are things like 1, 2, 3, 4. These are the Arabic numerals. We're not doing that. We're using the Roman numerals. I, I, IV, V, VI, etc. You should never have anything more than a charge of 6. So you don't need to know any more than that for chemistry. Great. Great. So for naming formula units, these are our rules. This is what we do every time. Okay? And now we have to add a new piece. Piece 6 for hydrates. If hydrated, we need to use prefixes followed by the word hydrate. For example, we might do pentahydrate. And how many waters would that be? It would be 5 waters. 5, or sorry, dot 5 H2O. Great. Okay, one other thing here to mention. If you look under practice, looking at 1A, you'll notice that we've got Na,C2H3O2 dot 3H2O. Now, in your mathematics class, what does that dot mean? Of course, it means to multiply. Here, it is not multiplication. We are not multiplying. It's denoting the chemical bond. It's denoting that there is a chemical bond here. So please do not say, oh yeah, this is sodium acetate times 3 water. That's not correct, right? Sodium acetate trihydrate. Trihydrate, okay. Before we go any further, I want to just verify that that is actually acetate. Yes, it is actually acetate. Excellent, okay. So here's what I want you to do now. I want you to do practice number 1. I want you to pause the video and come back to me once everyone has completed practice 1A, B, and C. Maybe take 2 minutes. Ready, go. All right, hopefully you're back with me now. Let's go through some of these answers. Well, I already told you the first one because I said it. It is sodium acetate trihydrate. Sodium acetate trihydrate. Let's look at the next one. Barium hydroxide octahydrate. Barium hydroxide octahydrate. Lastly, this one was a little trickier. This is cobalt 2 chloride hexahydrate. How do we do? Go ahead and make any corrections that you need to. Great. Excellent. So here's what I want you to do now. I want you to do number 2, A, B, and C, and then come back. Okay? Go ahead and pause the video now and do that. Maybe 2 minutes. All right, hopefully you're done. Now, for those of you who really struggled, I want to remind you of how we go about going from the name to the formula for our ionic compounds. All right, so here's what we do. First things first, we're going to write the symbol for the cation. Then we're going to write the symbol for the anion. We're going to write the oxidation numbers. And then we're going to crisscross. Lastly, simplify if we need to. So if we take our first one, calcium chloride dihydrate, we'll list our symbol for the cation, Ca. We'll list our symbol for the anion, Cl, and we'll write our oxidation numbers. Calcium is in the second column, which means it will always have a positive 2 charge. Chlorine is in column 17. It's in group 17, which means it will always have a negative 1 charge. When we crisscross, we're going to get Ca1, Cl2. And then we have a dihydrate, which means we are going to need to do a dot, 2H2O, just like that. Just like that. All right, so the answer for A is CaCl2.2H2O. The answer for B, so it's a little tricky, NH42C2O4.H2O. Some of you may put a 1 here. Remember, you don't really need to put 1s. Right? The 1 is implied by you having it there in the first place. So don't put 1s. Great. Lastly, for the third one, we have FePO4.6H2O. How'd that go? Pretty good, I hope. Awesome. Great. Well, let's move on to question 3. Question 3 asks you to calculate the percent of water in each of the following hydrates. All right, so what do we need to know in order to accomplish this one? Well, the important thing here, I'm not periodic table out of the way. The important thing here is that we remember the definition of a percentage. Right? The definition of a percentage is going to be the part over the whole times 100. You can kind of see where I'm going with this. When we're asking for the percent of water, we're asking for the mass percent. Asking for the mass percent. Does anyone have any ideas about how we might do that? Well, we're going to find the total number of water molecules, convert that into grams per mole, and then we're going to find the molar mass of the entire substance. And we'll take the molar mass of just the water divided by the molar mass of everything. So let's do 3A together. So for 3A, we've got sodium carbonate decahydrate. Well, we're going to do our naming. Our formula writing. First, what is the symbol for sodium? It's Na. And what is the symbol for carbonate? That's on your polyatomic ion sheets. It's this one right here. I don't know if you can see that very well in the video, but it's CO3 2-. All right, what's the oxidation state of sodium? Well, sodium is in group 1 in the alkali metals, and so it's going to be +1. Then we'll crisscross, and we'll get Na2CO3. And now we are a decahydrate, which means that we'll do a dot, 10H2O. Great. So the first thing we're going to do is we're going to find the molar mass of this whole thing. Molar mass of the whole thing. So the molar mass of sodium can be found on our periodic table, right? It's right here, 22.99. So we'll do that, 22.99. And now we have 2 of them, so multiply that by 2. Then we'll add the molar mass of carbon, which is over here, 12.01. And there's only 1 of them. And then we'll add the molar mass of oxygen, which is 16.00, and we have 3 of them. And then we'll add, remember this is chemically bound, we'll add the molar mass of hydrogen, which is 1.01, multiplied by the number of hydrogen we have. How many hydrogen do we have here? You may have said 2, you may have said 10, but both of those are incorrect. The actual number is 20. I have 10 waters, each of which has 2 hydrogens. There are 20 hydrogens total here. And lastly, oxygen once more, and this time we have 10 oxygens. So we'll add that up, and we'll get the molar mass of our sodium carbonate decahydrate. I'm going to pull out my calculator and do that now. Why don't you do the same? All right, hopefully you've done that, and like me, you've gotten 286.19 grams per mole. Great. So this is the whole. This is the whole. But the question here is asking, what is the percent of water in each of the hydrates? So now we need to compare this to the part, to the amount of water that we have. And that's going to be this portion right here, right? And so what we can say is if the mass percent is the part over the whole times 100, then we can take 20 times 1.01 plus 10 times 16.00, and we get this part right here is just 180.2. Alternatively, you could have taken the molar mass of water, which is 18.02, and you could have multiplied that by 10, which would have given you the same thing. Great. And then we'll take the part, which is 180.2, and we'll divide it by the whole, which is 286.19 times 100. And when we do that, we will get 62.96516.3%. All right, let's go ahead and take a look at a couple of things. In this case here, I've got 3 significant figures. In this case here, I've got 4. Right, but what I'm doing here is I'm adding up as my last, it's the last thing that I'm doing because of PEMDAS. And so because of that, my answer needs to go to the 100ths place, which means that it's actually this. So that's my mistake there. Now I've got 5 significant figures here, 5 significant figures here, and that means I'll want 5 in my answer, 62.965%. Usually I'm just going to ask you to please go to the 100ths place. 100ths place is fine here for these kinds of questions, and I'll note that in our assessments. So it would have been fine if you said 62.97%. And that's our answer. All right, here's what I want you to do now. I want you to try 3B on your own. Let's take 1.5 minutes to do that. Ready, go. All right, hopefully you've been following along with me well enough to get to the point where you have calculated out the molar mass of barium hydroxide octahydrate. You've been able to calculate how much of that was water's molar mass, and then you've divided the molar mass of all of the water divided by the molar mass of the total hydrate times 100 to get 45.69%. Excellent. Great. Let's move on to number 4 now. We're cooking with gas. This is great, right? Looking here at number 4, we have a hydrated sodium tetraborate, commonly called borax. Chemical analysis indicates that this hydrate is 52.8% sodium tetraborate and 47.2% water. Determine the formula and name the hydrate. All right. In order to name the hydrate, we need a couple of things, right? We need the name of the substance and its formula, right? This is going to be sodium and tetraborate. And if we grab our polyatomic ion sheet, we can see that tetraborate is right here, B4O72 minus. And we can crisscross and we can say, okay, we've got Na2B4O7, and then we've got a certain amount of water, a certain number of moles of water. XH2O. Sorry, that's a really terrible X. Right? And this is what we're looking for. We need this guy in order to finalize the name of the hydrate. And the way we're going to do that is exactly how we did empirical and molecular formulas, right? If we have 52.8% sodium tetraborate, 2P4O7, and we have 47.2% water, what can we do to appropriately solve this problem? Well, we can assume 100 grams. And when we do that, we can say, okay, I have 52.8 grams of sodium tetraborate. And I've got 47.2 grams of water. And then all we have to do is convert this into moles. And we already know how to do that, right? We need to find the molar mass. Well, the molar mass of water is really easy. We've been using it a lot today. It's 18.02 grams of water in 1 mole of water. But sodium tetraborate is a little bit more complicated, right? But we know how to find that. That's no problem. The molar mass of sodium is 22.99 grams per mole, and we have 2 of them. The molar mass of boron, I don't have that on the top of my head. We got to look at our periodic table, is 10.81. And we have 4 of them. And the molar mass of oxygen is 16.00, and we have 7 of them. So we'll grab our handy-dandy calculators, and we'll say 2 times 22.99 plus 4 times 10.81 plus 7 times 16.00, and that's going to get us 201.22 grams per mole. Because we want to get rid of grams, grams has to go on the bottom, so that's 201.22 grams of sodium tetraborate in 1 mole of sodium tetraborate. And now we just convert to moles. So we've got 52.8. Go ahead and do this with me. 52.8 divided by 201.22 gives us 0.262 moles. Similarly here, we'll do 47.2 divided by 18.02, and that's going to get us 2.62 moles. Does anyone remember what to do now? What do we do now? If you said we needed to divide by the smallest number, you'd be correct. In this case, that's going to be 0.262. And you should see that we get 1 mole of the sodium tetraborate and 10 moles of water. So what does that mean? That means that when we go to write out our formula, we know, so we wrote it over here earlier, we know that we have Na2B4O7 dot XH2O. What's that X? It's 10 moles H2O. How would we name this then? We would name this sodium tetraborate decahydrate. Great. Well, let's look at the question again because we've done a whole bunch of steps. Let's make sure we've done everything. It asks us to determine the formula and name the hydrate. Have we determined the formula? Yes, right here. Perfect. Have we named the hydrate? Yes, right here. Perfect. All right, that's our answer. So let's go ahead now and go to number 5. Number 5 says the data table below shows data from an experiment to determine the formulas of a hydrated barium chloride. Determine the formula for the hydrate and the name of the hydrate. Okay, so let's take a look here and see what we can deduce. We have the mass of an empty crucible, and we have the mass of a hydrate and a crucible. We have a blank for the initial mass of hydrate. We have mass after heating and a mass of anhydrate. Okay, so here's what's happening here. Hope you don't mind. I'm going to continue to use this piece of paper. Okay. Here's what's going on. We're going to take a crucible. Crucible is a small, rounded dish that's meant to be heated. And we're going to put it on a pipe stem triangle. I'm not even really going to try to draw this too well, but it's going to be held on a pipe stem triangle, which is going to be held up by an iron ring stand. Okay, and on that iron ring stand, we're going to have a little Bunsen burner. Can you see why I did science and not art? Okay, we're going to light a little flame here. And what's going to happen is we're going to heat up the hydrate that's in that crucible. Great. When we're done doing that, what's going to happen is all of the water is going to be driven off. Sorry, it's H2O, not 2HO. H2O. All the water will be driven off. In fact, when I come back in a couple of days, we're going to do this experiment together. Right, you're going to actually determine the mass percent of your substance, which is pretty cool. Okay, so we start off with barium chloride. Right, barium chloride. Barium is 2+, and chlorine is 1-. So when we crisscross, we get BaCl2 dot XH2O. Okay, and this is what we're looking for. We take our hydrate and we add heat to it, and the water is driven off, and we're left with just the barium chloride, the anhydrate, the anhydrous barium chloride. Great, so let's look at our data chart again. Go ahead and look at that. I have the mass of the crucible without anything, and I have the mass of the hydrate and the crucible together. Okay, let's call the mass of the crucible, let's call that X. And let's call the mass of the hydrate H. Okay, how do I find the initial mass of the hydrate? Well, that's like saying I've got the mass of the empty crucible, and I've got the mass of the crucible and the hydrate. Okay, all we have to do is subtract, right? And when we do that, we're going to get just the mass of the hydrate. Okay, so this is going to be 31.35 minus 21.30. So how much hydrate are we starting with? We're starting with 10.05 grams of barium chloride of an unknown hydrate. Great. So then we heat it. And when we heat it, all the water goes away. Bye. See you later. And what's going to happen is we're going to be left with a certain amount of anhydrate. The anhydrous form of the hydrate, just the salt. Cool. So how are we going to calculate that? Well, we're going to do exactly what we just did. We're going to do the mass of the mass after heating, which is 29.87. Plugging this into my calculator as we go. And we're going to subtract that from the mass of the crucible, 21.30. And we're going to get 8.57 grams of just barium chloride. There is no water. Great, so in that last little box there, under mass of anhydrate, I want you to write the mass of the water. How much water was driven off? Okay, if your thought is to subtract these two numbers, you'd be right. So 10.05 minus 8.57 gives us 1.48 grams of water. Okay, now you should be able to determine the formula for the hydrate and name the hydrate the same way we did up here. I want you and your neighbor to go ahead and work on this now. 2 to 2.5 minutes. Ready, go. Okay, so hopefully you've been able to do this with your neighbor. Okay, and hopefully you've done it the same way that we did it before, right? So what we do here is we take the amount of anhydrate, amount of water, and we convert that into moles using the molar mass. Then we divide by the smaller number and we get the mole to mole ratio. In this case, that's 1 to 2. This is very, very close to 2. And so what we'll do then is we'll say, okay, I have BaCl2 dot 2H2O, which is barium chloride dihydrate. Great. Let's look at the question again, make sure we answered everything. We need to determine the formula for the hydrate and the name of the hydrate. Have we done that? Yes, we have, and we're done. All right, here's what I want you to do now. Without any help, without any intervention from me, I want you and your neighbor to attempt question 6 together. Let's take no more than 5 minutes. Let's try to get this done as quickly as we can. You have all the tools you need. Go ahead and pause the video and I'll be back with you in a minute to go through it. All right, welcome back. Hopefully you've had a chance to do this together. So here's what I did. First, I went ahead and said, okay, 5.061 grams of hydrate minus 2.472 grams of anhydrate should give me 2.589 grams of water. Great, from there, I went ahead and I calculated the number of moles of anhydrate that I had and the number of moles of water that I had. I divided by the smaller number of moles to get a whole number mole-to-mole ratio, which I found to be 1 to 7. Then I could write out my chemical equation, MgSO4.7H2O. Wonderful. And what do we call that? We call that magnesium sulfate heptahydrate. Magnesium sulfate heptahydrate. Awesome. Well, this ends the video. You should have some practice to do in terms of mole calculations. I believe there's a mole quiz next class. Right, feel free to reach out to me if you have any questions. This here endeth the lesson. Hope you all have a great day. Looking forward to seeing you all again next week. Take care.